much. I'm grateful to the organizers for giving me a chance of this talk. Since I have 15 minutes, I choose only one topic. In this talk, we consider the Gauss maps of surfaces in the Euclidean 4 space and E42, the four-dimensional flat neutral space form. In addition, in general, we consider surfaces in hyperkähler for manifolds and neutral hyperkähler for manifolds. In the first section, we consider minimal surfaces in hyperkähler for manifolds. Let M be our Riemann surface, and let F be a conformal and minimal immersion of M into the Euclidean 4 space, E4. Let GF be the Gauss map of F. The target is the product of CP1 and CP1 itself. This theorem is well known. The Gauss map is holomorphic. Let N be an oriented Riemannian for manifold. Then we have this bundle decomposition. This bundle is of rank 3, of rank 6, and these two subbundles are of rank 3. We can obtain this bundle decomposition and not seeing this double covering. These subbundles are locally generated by these sections. Omega ij is given by ei which ej, and E1, E2, E3, E4 form a local ordered orthonormal frame field of the tangent bundle Tn, giving the orientation of n. If n is hyperkähler, then one of these two subbundles is a product bundle. If n is given by the Euclidean 4 space, then both subbundles are product bundles. We denote by these. The twistor spaces associated with n. These are the unit sphere bundles of these bundles. Let F be a conformal immersion of a Riemann surface M into N. We denote by these. Sections of the twistor spaces associated with the pullback band of Tn by the immersion F, defined by these. Xi1, Xi2, Xi3, Xi4 form a local orthonormal frame field such that Xi1 and Xi2 are tangent to the surface, so that this gives the orientation of M. If N is hyperkähler, so that this bundle is a product bundle, then we can consider theta F plus to be a map from M into CP1. Then we can obtain this theorem. Suppose that N is hyperkähler and that F is minimal. Then one of these two sections is holomorphic map from M into CP1. So we can consider theorem 1, this theorem, to be a corollary of this theorem. I explain a proof of theorem 1, 2. Suppose that this subbundle is a product bundle. Then we can suppose that so plus. We denote by theta plus 1, theta plus 2, and theta plus 3 are horizontal. We can suppose. These sections form an orthonormal frame field of this bundle. Let GF plus be a CP1 valued function satisfying this equation. If we set this psi I, EI, then we obtain this representation of GF plus by psi 1, psi 2, psi 3, psi 4. Suppose that f is minimal, then we obtain this equation. Let omega ij be the connection forms of the Levitch connection with respect to frame E1, E2, E3, E4. Then we immediately obtain this relation. In addition, since these are horizontal, we suppose, then we have these three relations. In addition, this equation means these four equations. Using these relations, we can obtain this. This means that theta f plus is holomorphic. In this section, we consider space-like surfaces with domain curvature vector in neutral hyperkähler for manifolds. Let N be an oriented neutral for manifold. So its metric H has signature to 2. Then we have this bundle decomposition, noticing this double covering. These two subbundles are locally generated by these sections. Notice that the signatures are minus plus, not plus minus. If N is a neutral hyperkähler, then one of these two subbundles is a product bundle. If N is equal to E42, the four-dimensional flat neutral space form, then both of these two subbundles are product bundles. Let H hat be the metric of this bundle induced by H. Then H hat has indefinite metric and signature 2, 4. And the restrictions of H hat on these two subbundles have signature 1, 2. We denote by these fiber bundles of these two subbundles satisfying this condition. We call these fiber bundles the space-like twistor spaces associated with N. Each fiber is given by a hyperboloid of 2 sheets. Let F be a space-like and conformal immersion of a Riemann surface into N. We denote by theta F plus minus sections of the space-like twistor spaces associated with the pullback bundle of Tn by the immersion F, defined by these. Where Xi1, Xi2, Xi3, Xi4 are as in section. Pseudo-orthonormal. If N is neutral hyperkähler, so that this bundle is a product bundle, then we can consider theta F plus to be a map from N into the complex one-dimensional hyperbolic space, CH1. Then we can obtain this theorem. Suppose that N is neutral hyperkähler and F has zero mean curvature vector. Then one of theta F plus, theta F minus is a holomorphic map from M into CH1. As a corollary, we have this. Let F be a space-like and conformal immersion with zero mean curvature vector into E42. And GF, the Gauss map of F. The target is the product of CH1 and CH1 itself. Then the Gauss map GF is holomorphic. In the last section, we consider time-like surfaces with zero mean curvature vector in neutral hyperkähler for manifolds. We denote by these fiber bundles of these two subbundles. N is oriented neutral for manifold. These two subbundles have fiber bundles satisfying this condition. Since H hat is indefinite, this value can be negative. We call these fiber bundles the time-like twistor spaces associated with N. Each fiber is given by a hyperboloid of one sheet. Let N be a Lorentz surface. This means a two-dimensional manifold with a holomorphic system of paracomplex coordinate neighborhoods. This neighborhood is an open set of the paracomplex plane. Let F be a time-like and conformal immersion of M into N. We denote by theta F plus minus sections of the time-like twistor spaces associated with the product bundle, defined by these. Xi1, Xi3, Xi4, Xi2. Xi1, Xi3. Xi1 is space-like. Xi3 is time-like. These are tangent to the surface. If N is neutral hyperkähler, so that this is a product bundle, then we can consider theta F plus to be a map from M into C tilde H1. We denote by this a hyperboloid of one sheet as a Lorentz surface. A hyperboloid of one sheet is now given by this. Let R plus R minus be open subsets of a hyperboloid of one sheet, defined by this. R plus is given by the point of H21 satisfying this. The third component is not equal to 1. R minus is given by this condition. The third component is not equal to minus 1. We see that R plus R minus form a system of paracomplex coordinate neighborhood of H21 by using the stereographic projection. This figure expresses the geometric definition of stereographic projection from 0, 0, 1. This is H21, a hyperboloid of one sheet. At each point, for each point P, the stereographic projection PR plus gives a point of the x1, x2 plane like this. Then we see that this composition is holomorphic as a paracomplex valued function of one paracomplex variable. Then we can consider H21 to be a Lorentz surface, which is denoted by C tilde H1. We can obtain this theorem. Suppose that N is neutral hyperkähler and F has zero mean curvature vector, then one node theta f plus theta f minus is a holomorphic map from N into C tilde H1. As a corollary, we can obtain this. Let F be a time-like and conformal immersion with zero mean curvature vector into E42. And GF, the Gauss map of F. The target is the product of C tilde H1 and C tilde H1 itself. Then the Gauss map GF is holomorphic. I have finished my talk. Thank you very much.